So we will begin talking about the Lagrangian and Hamiltonian formulations of the electromagnetic field. Now the action for a relativistic point particle of mass m is given in equation 1.1. So this expression says that the action is equal to negative of minus mc, which m is the mass, c is the speed of light, and times the integral over of ds, and this integral is over gamma, so where gamma is the word line of the particle. Now here ds is defined as in expression 1.2, so it's the square root of minus or square root of c squared dt squared minus dx squared. So now if you will notice, this expression is positive only for paths which are either time-like or null. So in other words, if you draw the null cone or the light cone for any given observer, then this action refers only to those paths which at no point have a slope which is greater than 45 degrees in the space-time diagram. And here, of course, it is understood that the time axis has been scaled by a multiple of the speed of light. Now the question is, how do we couple a point particle to an electromagnetic field? Now we know that an electromagnetic field can be written in terms of we know that an electromagnetic field can be written in terms of a 4-vector potential whose time-like component is the regular scalar potential divided by c, and whose space-like components are the the vector potential which you are familiar with. So I here index runs from 1 to 3, and A is our usual vector potential. So what we have to do now is we have to figure out some way of incorporating this vector potential and combining it with the action for a relativistic point particle which we had written down earlier in equation 1.1. So how do we do that? Well, let's think about this for a second. A mu is a 4th vector, but it's also a field. What does that mean? Well, it means that the components of A mu can change from point to point. They are functions of space coordinates and of the time coordinates, right? So there is no reason for either the scalar field or the vector field to be a constant. These are in general functions of space-time, right? Functions on space-time. So as a particle moves through space-time, it interacts with the 4-vector field at each point. So for instance, here at each point along the trajectory of this particle, the 4-vector takes some value, right? And this 4-vector interacts with the particle in some manner. And so the question is, how should it interact? Well, so now we come to the concept of writing down the expression for the Lagrangian based entirely on the symmetries allowed symmetries of the physical problem in question. So what are the allowed symmetries here? Here we have the following symmetries. We have Lorentz symmetry, right? So that means, according to this, the action should be a Lorentz, a scalar, or it should be invariant under Lorentz transformations. Right? So now if you look at the action that is given in equation 1.1, it is obviously a scalar because it's a function only of the space-time interval, and that is a well-known Lorentz invariant. But now what we have to do is we have to write down something which involves this 4-vector potential A. And now we have this expression for the action. Now the question is, what should we do to incorporate A mu? Well, as I said earlier, A mu interacts at each point with the particle, right? Now how would it interact with the particle? Well, think about this for a second. A mu is a 4-vector. We need to make a term out of this 4-vector. We need something which is a scalar. So we need a scalar. How do we make a 4-vector? How do we take a 4-vector? So if we are given any 4-vector, how do we get a scalar out of it? Right? So we know how to do that. We just take any other 4-vector and contract it, and this just becomes a scalar. So if we have this 4-vector A mu, and it is defined at every point along the path of the particle, then we just have to contract it with some other 4-vector V mu, which is also defined along the path of the particle, and this will. So once we do this contraction, we get a quantity which is a Lorentz scalar. And using this Lorentz scalar, now we can write down an action for our particle interacting with the gauge field. So we will write that as, let's say, SEM as integral A mu V mu, and the integral is done along the word line of the particle, and there will be some coupling constant which turns out to be equal to the charge of the particle divided by the speed of light. Now, so the total action for a relativistic point particle moving under the effect of a electromagnetic field becomes minus mc integral ds minus q by c integral a mu v mu d gamma. Now the 4-vector, velocity 4-vector, can be written as dx mu by d gamma, where gamma is the quantity which parameterizes points on the word line of the particle, and so the electromagnetic action becomes minus q by c integral a mu dx mu by d gamma. So this just becomes minus q by c integral a mu dx mu, and then our final action is the same as before, only with a small modification, which is this. So now let's give these equations some numbers. So we have 1.1, 1.2, and then so let's call this 1.3, and we'll call this 1.4. Alright, now, so this is the action. Now let us look at this a little bit more carefully. The length element ds is equal to square root of c squared dt squared minus dx squared. So this can be written as c dt square root of 1 minus dx by dt squared, which is equal to c dt times root of 1 minus v by c squared, or I can write that as c dt by gamma. So this is equal to ds, and dx mu is just the infinitesimal displacement along the path of the world line. So that is just going to be equal to c dt and then dx dy dz. So now our action becomes minus mc mc square and dt by gamma and minus q by c integral of a mu dx mu. So now what is a mu dx mu? Is the dot product of the 4 vector corresponding to the electromagnetic field with the 4 vector corresponding to the infinitesimal world line displacement. So this becomes minus phi dt plus a dot dx. And once again, I can take dt common and write this as minus minus dt into phi minus a dot v. So our action is minus mc square dt gamma minus q by c integral of, so now we can write this as a plus sign, phi minus a dot v times dt. So the benefit of doing this is the fact that both the terms now become integrals over dt. So we can collect all of these different terms in one expression, and we can write the full action as minus mc squared integral of 1 by gamma q by c phi minus a dot v, and this is integrated over the world line. So small typo here, so this should be and so this is the final form of the action. The benefit of writing the action in this manner is that we can now identify the term within the brackets as the Lagrangian of the system. So the Lagrangian is given by this term, and so let us number these equations again. So 1.5, 1.6. Now once you have the Lagrangian, Now you can use the standard machinery of Euler-Lagrange to calculate various quantities. So one of those quantities is the canonical momentum or the generalized momentum. So P. So or if you want to be even more careful, let's say Pi. So the ith component of the 3 momentum. Now technically at this point you might ask, well, why am I evaluating Pi? I'm working in a Lorentz invariant fully relativistic framework, so why am I not evaluating P mu? So we will see what the answer to that will be shortly. So for the time being, let us continue with evaluating Pi. So Pi will just be equal to dl by d of the derivative with respect to xi dot. What is xi dot? Xi dot is equal to dxi by dt, or more simply the vector p is equal to dl by d v. Now writing it in this form allows us to easily do the differentiation, recalling that 1 by gamma is equal to root of 1 minus v dot v by c square, so which tells us that d gamma by dv is equal to, so if we take the derivative, we get 1 by 2 root of 1 minus v square by c square, and then when we again take the derivative, we get minus 2v by c square. So this is equal to minus v by c square times gamma. And so dl by dv will be equal to so small error, okay, equal to mc square times v by c square times gamma. And then we'll get another contribution from the electromagnetic part, and that contribution we can see will simply be minus q by c a. So and so finally we find that the momentum, the canonical momentum associated with this particle becomes mv gamma minus q by c a. So now here we notice one interesting thing. The first term is the usual relativistic momentum for a point particle, right? So it's mv, non-relativistic momentum, multiplied by the Lorentz factor gamma. But now we have an extra term, and this extra term is coming from the presence of the electromagnetic field. So we can refer to this as the electromagnetic momentum, and we will see what the consequences of this are shortly. Now, once we have the momentum, we can calculate the Hamiltonian using the Legendre transform, which connects the Lagrangian to the Hamiltonian. And what is the Legendre transform? Well, it tells us that if you have some set of canonical variables p and some q, then this is the relationship as given by the Legendre transform. So in our case, the canonical variables q is simply the space-time, the spatial position of the particle, and so this just becomes p dot v minus L. And what is p dot v? We can see that that is equal to m gamma v square minus q by c a dot v. And what is L? L is this expression, so we can just copy and paste it here. And so we get a plus sign here and a negative sign here, and the total sum of both of these becomes let's see, m times gamma v square plus c square by gamma square. And then we can see that the term which involves the vector potential will cancel out, and we will be left with q by c times phi. And so we have the Hamiltonian is equal to m gamma v square plus c square into 1 minus v square by c square q by c phi, which is equal to, and so again we have some cancellations, so these two terms will cancel. We will be left with mc square gamma minus q by c phi as our Hamiltonian for a particle interacting with an electromagnetic field. Let us pause for a moment and gather together all the facts that we have discovered so far. One is this expression for the Lagrangian. The other is the expression for the momentum of the particle, the canonical momentum one, I should say. So to distinguish the canonical momentum from the mechanical momentum, I will use capital P for the canonical momentum and small p for the mechanical momentum. And then we have the form of the Hamiltonian, which is alright. So we have a Hamiltonian, we have a canonical momentum, we have the Lagrangian. But now we see that the Hamiltonian as written in 1.11 does not seem to have any dependence on the vector potential. And also it is not expressed in terms of the momentum of the particle. So we want to remedy this. So let's see how one might go about doing that. Well, if you look at 1.9, we see that the mechanical momentum of the particle can be written as the canonical momentum plus this q by c times the vector potential. And similarly, from 1.11 we see that the total energy of the particle can be written as the Hamiltonian plus q by c times phi. And now we know that for a relativistic point particle, the mechanical momentum and the energy are related by the following expression, which is so we can simply insert the results from the previous line into this one, and we find that h plus q by c phi whole square is equal to canonical momentum q by c times a square plus mc square whole square. And so finally the expression for the Hamiltonian of our particle becomes, by taking the square root, you can write it as q by c a square mc square whole square minus q by c times phi. So this is the expression for the Hamiltonian. Now this is the Hamiltonian for a relativistic particle interacting with an electromagnetic field. For most practical purposes, we are interested in the case when the particle is non-relativistic. In this case, there will still be an interaction with the electromagnetic field, which one can get from 1.14 by taking the limit that v by c is much less than 1. And so how do we do that? Well, let's look at the Lagrangian. So once again, in the Lagrangian we have the term mc square by gamma, or minus mc square root of 1 minus v square by c square. So in the non-relativistic limit, this expression can be Taylor expanded as 1 minus 1 half v square by c square plus order v4 by c4 terms and more. And so this becomes minus mc square plus 1 half mv square plus higher order terms. And so then our Lagrangian becomes L is equal to minus mc square plus 1 half mv square plus the electromagnetic contribution. From this we can, so we'll put a non-relativistic NR here to indicate the fact that this is a non-relativistic Lagrangian, and from this we can obtain the canonical momentum again by following the same procedure. So now we will get mv minus q by c times a, which is our usual mechanical momentum p minus q by c times a. And we can see that this expression is formally identical to what we had earlier, where instead of our non-relativistic momentum, we were using the relativistic momentum, which was gamma mv. Here it has just become reduced to mv, and gamma has been taken to be 1. And now the Hamiltonian similarly can be written as p dot v minus L, and so that becomes mv square minus q by c a dot v, and then plus mc square minus 1 half mc square q by c phi plus q by c a dot v. And then once again we have the same cancellations we did previously, and our final non-relativistic Hamiltonian becomes mc square plus 1/2 mv square minus q by c phi. Now in this Hamiltonian we can see that mc square is simply an additive constant, so we can throw it away and we are left with our non-relativistic Hamiltonian, which is 1/2 m v square minus q phi by c, which can also be written as our mechanical momentum squared by 2m. And referring back to the expression for the canonical momentum, this can be written as the canonical momentum plus q by c a dot v squared minus q by c phi. So finally we are left with this expression for the Hamiltonian of a particle interacting with an electromagnetic field, and which is non-relativistic. And now 1.17, there was a small error in that I had put a dot v. There is no a dot v term, it's just a. So the correct expression is shown here in 1.17. So the non-relativistic Hamiltonian is given by 1 by 2m brackets capital P, so that's the canonical momentum, plus q by c plus the spatial vector field whole brackets close whole square minus q phi by c. Now if you refer to any of the textbooks like as I have been doing, you will see that the expression that is presented in most of these textbooks is slightly different. It has a sign difference in front of the components of the 4 potential. So let me write this as 1.17 prime. Now how do I get 1.17 prime? Well, the solution can be traced back to the expression for the action for a particle interacting with an electromagnetic field, and if I take this sign here to be a positive sign instead of a negative sign, then everything will turn out to be so the vector potential, the 4 vector potential will basically, you can take it to minus mu, and doing that gives you the expression 1.17 prime. Now just to mention, what are we allowed to do this? Are we allowed to take the vector potential to its negative, or in other words, are we allowed to perform this operation of parity, changing the parity of the vector potential? Well, we will see later that the Lagrangian for the electromagnetic field, which is just the pure electromagnetic field, will have the form minus 1 by 4 f mu nu squared, where f mu nu is the Maxwell field strength tensor, and under the change of sign of the vector potential, the field strength, you can also see, changes sign. However, the Maxwell Lagrangian, which involves the square of the field strength, remains the same. So there is no effect of the change of this sign of the vector potential on the equations of electromagnetism. So as long as you reverse the sign of both the scalar potential and the vector potential at the same time, you get the same physics. Of course, this is no longer true if you add matter into the situation, into the picture. Why is that? Because then, if you want to add matter, the action for your system will be modified and will look like this. So here, the first part is the pure electromagnetic part, and the second part describes the coupling of the 4 vector potential with J mu. And what is J mu? J mu is the current density 4 vector. So it's gamma rho comma it's rho j. I think I'm missing a factor of c somewhere, but anyway, this is the current 4 vector, and this coupling makes sense, right? Because, well, first of all, this term, as is clear, is Lorentz invariant. One can see that it's just a contraction between 2 4 vectors, so that is a scalar, so that is a Lorentz invariant object. So if you do this, then of course, under the change of a sign in the vector potential, this term will also pick up a negative sign, and so your action will no longer be invariant. So then if you want to keep your action invariant, you have to also change the sign of your current 4 vector. So what does this mean? Well, this means that if you want to get the action with the right sign and everything, well, you have to start with the correct action. So that means here one has to put a plus sign at the very beginning. And so finally, let me write down the action for a point particle coupled to an electromagnetic field, and which is given by this expression. And let us update our equation numbers once. So this is 1.18, and let's call this 1.19, and then this, let's give it another label as 1.20.